And the soft cutting means when after cooling particles combines and they form a low momentum transfer. And in soft cutting, mostly there is a production of low energetic particles. Relevant for our research is that we have to study the correlation between the LHC energies and we have to check their particle production, and then we will also focus on the jet production. So in our result we are using the Hydrogen, which is a Monte Carlo event generator. Basically this is used for the synthesis of high energy particles. Okay. So importance for Hydrogen in our case is first of all for jet analysis, because more there is a combination of both soft scattering as well as hard scattering, means soft process also produces along with the hard processes. So using Hydrogen model we can easily visualize both soft as well as the hard processes. So applications in our study is that we are using Hydrogen model in our research to simulate the PP collision, okay, and to study the multiplicity, pseudo rapidity, and the transverse momentum. And basically, the Hydrogen model is crucial and important for the experimental high energy physics. So the methodology we are using is we have to investigate the charged particle production in TP collision, and we are using three different energies: the minimum energy, which is 0.9 TeV, the middle energy, which is 11, and the max energy yet achieved, which is 13 TeV, using the Hydrogen model. So for that, first of all, we have to set the center of mass energies, which I mentioned. Then we have to set the collision system. In our case, we are using proton and proton, and then we have to specify the number of events to just check the statistical significance. And then we have to set parameter. After setting parameter, we can book the histograms for multiplicity, pseudo rapidity, and the transverse momentum. And after that, we have to also check the jet analysis. We are varying our jet as one time we are using jet on. Then we also check by jet set F off, and also by setting the value of jet 1 to check the different circumstances of the multiplicity and the transverse momentum. Multiplicity, which my groupmate already mentioned, which is the total number of particles produced after the collision, and pseudo rapidity, which is the angular distributions of the particles, and the transverse momentum, which is basically the momentum of the particle produced in with the beam axis. Now I will discuss the results and discussions. So first of all, this is our multiplicity results in TP fusion. As you can see, events with the events with the low number of particles are produced more. Okay, in all these cases, this graph is for 0.9 TeV energy, this graph is for 7 TeV, and this for the max energy for 13 TeV. But the events with low number of particles are produced more. But by increasing the amount of energy, we can easily visualize that the peak goes up, means that the particle production now increases. Also, by increasing the amount of energy, the tail distributed along, means that the number of particles produced more in case of multiplicity. Now, let's check the jet dependence. Whenever jet is set as on, we can see we got a broader distribution because our jets are high PT particles. So when jet is on, so we get the events with high number of particles are produced more. Whereas when our jet is set as 1, we see there is an intermediate behavior in all these. And when our jet is off, this red curve shows we are getting only events which have low number of particles. So by initializing the number of jets, we can easily produce the more number of particles. These results we can find from this. Now, these are the results of pseudo-rapidity results in our PP collision. As you can see, this plot demonstrates that most of the particles produced in the central region, and this is approximately symmetric around the center at eta equals to 0. This is eta equals to 0. This is forward beam, means projectile beam which is coming. This negative beam means the targeted particle which is coming. They have to collide, and most of the particles produced in the central region. As you can see, different energies 9, 7, and 13 TeV. But by increasing the amount of energy, we can see here we are getting the density at 3. Here you can see up to 5, and here you can see up to 6. So by increasing the amount of energy, the density of the particles increased. means we are producing more number of particles by increasing the amount of energy. Also, you can see the width of the distribution also got long, means longitudinal distribution. So means particles more produced when there is high energy. You can see sharp peak and this is broader peak. Means that by increasing the amount of energy, the particles now produced more longitudinally around the central region. Okay. Now let's check the jet dependence. When our jet is on, this JD, this light distribution, again we are getting the high distribution. Means that more particles produced when your jet is set as on. Whereas when your jet is 1, we are getting again the intermediate behavior. And when there is no jet, we can see we are getting low density of particles in all these cases. So whenever there is jet inclusion, we can gain the more number of particle production, more density of the particles. Now this is our transverse momentum results in PP collision. Transverse momentum, which is the momentum of particle along the beam axis. As you can visualize from this graph, the graph decreases rapidly as we increase the PT value, means the transverse momentum. Okay, so as you can see, low momentum particles, we are getting peak at low momentum particles. Means that low momentum particles are most common than high momentum particles. There is only probability of the production of low momentum particles. But by increasing the amount of energy, you can see like 7 and 13, the distribution goes up, means that high momentum particles also now producing. So by increasing the amount of energy, we can easily produce the high momentum particles, means more energetic particles we produced. Jet dependence, as it is, as jets are high PT particles, so whenever jet is inclusion in our results, you can see we are getting high energetic particles. But when the jet is off this red distribution, you can see only low momentum particle produced, not high. Okay, because jet are high PT particles. Now these are the results which I already told you. In multiplicity, number of particles got increased as we increasing energy. Similarly, sugar rapidity, by increasing the amount of energy, we can easily the distribution got broader for the density of the particles, and transverse momentum and jet production is as it is. By increasing the amount of energy, we can easily produce the high energetic particles. So in future results, in future work, we can use different values of jet to analyze the jet production, and we can use other cooling systems, like we can use heavy ions, and definitely if there is an upgraded energy at LHC beyond 13 GeV, definitely we can use them. And we can also use advanced models in futures, like PTHIA we can use, and we can also do experimental data correlation, that we can compare our data with the LS experimental data results. Now the acknowledgement, thanks to our supervisor Dr. Lizman for their supervision, thanks to our course instructor Dr. Uzma for deep understanding of the particle physics, and thanks to Dr. Yasser Ali for their valuable counseling, and our friends and families. These are the reference to the images, and thanks. We sincerely appreciate your time and attention. We are grateful to giving us the opportunity to present our work, and I'm very grateful for any question or feedback from you.